Well, great. Thanks, Deanna, for keeping everything running here. I am very excited to introduce Mick Patel to give his senior experience talk today. I have, along with the rest of the seniors of this class, Mick and I have been neck and neck through our careers at Lawrence. And he was one of the first research students to join my group, and also one of the research students to do 2 summer stints working with me over a couple of summers. So when I first met Mick and had him in organic lab, I was not aware that he was a first year, but I was aware of how enthusiastic he was about what was going on in that lab class, including I can remember his reaction when he saw the NMR for the first time. I think he was the most excited student, at least in that year's class, when we were down in the NMR room. He was really paying appropriate reverence to the NMR. So I figured that would probably be good enthusiasm to try to, oh no, capitalize on. Sorry, am I still here? I'm still here. Okay, Zoom said it was gonna log me out here. Sorry, Mick. Anyways, I was glad to invite Mick into the lab after organic 1 and 2. And he has been working hard, as you're gonna see, doing that. And so I think it's a testament to Mick's teamwork that even coaches here for the track and cross country teams, and a bunch of team members from both the chemistry side of things and the sports side of things. So looking forward to hearing Mick's talk, and I'll shut up and let him have the floor here.
All right, thanks for the introduction, Graham. All right, hi everyone. My name is Mick, as Graham has introduced me. And I'm going to be doing somewhat of an informal talk today. I've given a lot of formal ones in the past and wanted to do something a little bit different this time. So here I present to you, oh, my clicker broke. Hold on just a quick second. I'll do it manually. All right. Here I present to you guys 3 years of hard work that I've conducted with Graham doing research, and also the personal experiences that I've had along the way. At times, this project has been very confusing and mysterious, and it's almost felt like we've been in this X-Files episode. And just the best thing I could do sometimes was blame it on the aliens. But I'm already getting ahead of myself. Let's start all the way at the beginning. When I first met Graham, he already explained this to you guys, but I was an Orgo student for him in the spring term of 2017. And he noticed that I had this enthusiasm for chemistry and invited me to join his lab. After that, he started explaining one of his projects to me, and he started with these types of molecules. These are stable radicals. Notice how each of these molecules have a dot on them, and that dot is a radical. It's a single unpaired electron. And radicals have this bad reputation going for them because they tend to be very reactive. So they've been known to cause the ozone layer depletion, but also have been indicated to cause cancer by mutating genes. So overall, not a good reputation for radicals, but we have ways of taming these things. And so here are 3 examples of these stable radicals. But what Graham is asking is, can we make these molecules emit light? So these molecules by themselves don't emit light, but if we modify them, can we turn them into molecules that can emit light? And these kinds of things would have applications in screen technology, specifically in OLED devices. OLED stands for organic light emitting diode. And the organic part of this is the most important because organic electronics are cheap and they're lightweight. And in the bottom left image, you can see they're flexible. They also have unique properties such as efficiency and better resolution than your traditional LCD and LED screens. Here's what the structure of an OLED looks like. Really, all we care about here is the emissive layer. It's composed of organic molecules and polymers that emit light. So if we're going to make something like a stable, luminescent radical, we would want it to go into something like in the emissive layer of an OLED. Here's where I learned the first lesson of my research. I was already hooked by the time Graham started talking about these things because he basically told me that I get to go into lab and make these molecules that glow. And what a cooler project could I have picked for this for these next 3 years, right? Well, I was totally ready to get up and walk out, shake his hand, and start working in lab. But I found out that, well, if you're going to ask a professor about their research, you're probably going to be there a while. Graham is super excited about what he does, and he just did not stop telling me about every single detail in this project. So he moved on, and he's like, well, why would we even choose radicals in the first place? To understand this, let's look at a non-radical system, a non-radical emitter. So this is a Jablonski diagram, which is a model for our understanding of how molecules produce light. This is the S0 state of the electron in a non-radical emitter. When we excite this electron with, say, UV radiation, it'll jump up to this higher energy SN state. From here, it'll wiggle away some of its energy and go into this S1 state. It's still high in energy. So it can jump back down into the ground state, this S0 state, and emit energy in the form of visible light. But it's also a very specific form of light called fluorescence. And fluorescence is this quick burst of light. The excited electron from the S1 state can also go through a process called intersystem crossing and go into this T1 state. From here, it'll also emit energy in the form of visible light, but it'll do it through a process called phosphorescence. And phosphorescence is a slow, timed release of light. If we're making something like a screen, this is not ideal because of two reasons. One of them is because of this time delay. If we want control over when the lights turn on and off, the phosphorescence is not ideal because there is a slow timed release. We want something that's much quicker, like fluorescence. And on top of that, phosphorescence and fluorescence occur at different colors. And so now we have a color interference along with this time delay. But if we take a look at a radical system, it is drastically different. We'll start back at this D0 state. It's this ground state of an electron. And if we excite that electron with some sort of UV radiation, it'll jump up to this excited DN state. From here, it'll relax away some of its energy into a high energy D1 state, and then jump back down to the ground state, emitting energy in the form of visible light, but only in the form of fluorescence. So now we don't have this phosphorescence interfering with our light emission. And we have a hypothesis, which is that radicals are more efficient at emitting light. If we're trying to make something like a screen, remember we want this control, this quick on-off, and we don't want any color interference from phosphorescence. And radical systems are predicted to be this exact thing that we want because it only produces fluorescence. Okay, now we have this hypothesis, we have a prediction of how radicals work, but we need to go in a lab and test out whether this is true or not. To do that, we're going to design a radical that can emit light. But first, we need to talk about how radicals can even be stabilized. And there's two main ways. One is through this physical stabilization. Here's a depiction of two electrons, and they're happily paired together. But if we pull one of these electrons away from the other, then the one that's left behind will turn into a radical. Now remember, radicals are this very reactive things. So they've completely wrecked our ozone layer, and they just want to rip apart anything that they touch to grab another electron again. But if we surround this radical with these big, bulky organic groups, we can create a physical barrier around the radical. So things like water and oxygen just can't get at the radical because these big, bulky groups are blocking them. Another way is through electronic stabilization. Whoa. All right, electronic stabilization. If we surround this radical with other electrons on different atoms, and then allow that radical to swap out with those other electrons, we can spread the radical across a bigger area. And now radicals are more reactive when they're sitting in one spot, so we want them to move around as freely as possible. All right, we have our two ways of stabilization. Let's take a look at a real example. This is BDPA. I already showed you this in the first slide, but here is the radical represented by the dot. Around this radical are these three bulky organic groups. And those organic groups do the job of physically blocking the radical. So it essentially encases the radical in the center. Also, there is an electronic stabilization here. So notice how there are double bonds that are spaced one apart from each other all across this molecule. and how the radical is spaced one apart from each double bond around it. This is a phenomenon called resonance. And resonance just means that the radical is free to spread across the entire molecule. Now we have our electronic stabilization, and we know that both forms of stabilization are present in this BDPA molecule. We can predict that it's a stable radical. And sure enough, it is. It was made in 1932, which is a really long time ago, and it's surprising that they made this. But when they tested it out, they found out that it just did not decompose, even for decades under certain conditions. And what better model for our study than a molecule that pretty much doesn't decompose? So let's use this as our model for this study. Now, BDPA doesn't emit light by itself, but we can modify it into a molecule that might emit light. So here is BDAA, it's the target for this research. We basically just swapped out this one ring right here with a molecule called anthracene. And anthracene is a chromophore. It's a molecule that's known to emit light when excited by UV radiation. All right, great. We have our target molecule. And now here's a quick summary before we move on, just of everything that I've covered so far. There are these stable radicals, and we want to make them emit light. So we need to modify them a little bit. They have applications in technology, specifically in OLED devices. And they're perfect for that type of application because they're theoretically more efficient than non-radical emitting molecules. And finally, we have that our target molecule is BDAA. At this point, 10 hours has passed. I'm still in Graham's office, but he's finally sent me away because I know everything I need to know about stable luminescent radicals. Now it's my job to go into lab and synthesize this molecule. So let's first break it into its components. So there in red is the anthracene component. And then in green and blue is the fluorines. Before I go on, I need to clear up this issue with fluorine. Fluorine with an I is an atom, and fluorine with an E is a molecule. I don't know what crazy scientists thought this was a good idea, but luckily I'm only going to be talking about the one on the right for the rest of this presentation. All right, so now it was my job to go and do this in lab, but it was my first year in lab. I was fairly inexperienced. I've only taken Orgo 2 as my most advanced class. And I needed to find a way to figure out how organic synthesis even worked. It was so complicated to me at the time. But luckily I found a really easy analogy for this, which is Lego bricks. If we take one Lego brick and add it to another, we get a brand new structure out of it. And just like that, in the step one of our synthesis, we're taking one thing, this anthracenal compound. So it's not actually anthracene because it's got this little extra bit on it. But essentially what we're doing is we're taking anthracene and adding it to fluorine. We have to throw in a couple of extra things. So above the arrow is potassium hydroxide, which is a base. It just makes the reaction go forward. And then below the arrow is the solvent. In this case is ethanol. The best way to understand the solvent is to think about baking a cake with water. So water allows the ingredients to mix together and bake properly. In this case, ethanol is allowing all these ingredients to mix together so that we can form this product out the other end. And it really just looks a lot like our Lego structure. So what greater analogy than that, right? Well, I found out that this reaction was just so cool by itself because it produced this yellow color. It was so cool to me at the time because I created something that was colorful. In this picture, you can see it's orange. Well, that's because in its crystalline form, it tended to look orange, while in its powder form, it looked yellow. And also, it luminesced bright yellow. This is exactly why I even did this project in the first place. So seeing this in my very first step of the reaction was super cool. I saw something that emitted light when excited by UV radiation. All right, now if you look at especially this wayboat right here, this thing is about the size of my hand. It's a pretty big wayboat, and it's completely filled with powder. So it must look like the reaction worked very well, right? Well, it turns out the more and more I did this reaction, the more and more I tried to get out this product, I realized that I wasn't actually getting what I wanted and that it was more difficult than I thought to get this product. I had absolutely garbage yields by the time I purified this thing. I had 15% maximum, and this was the best I've gotten over the course of 3 years. And most of the times I would get about 10% yield, so even worse than this maximum. What makes it even worse is that, well, other people have done reactions that were similar to this one, and I was just following what they did, but they got like 60 to 80% yield, and I was getting nowhere near that. The only two things I can think of is that there's something going wrong here, or that I was just a bad chemist. I'm gonna go with something that's going wrong here, obviously. The reaction itself took about 3 hours to 4 hours to run, but then after it was done, I had to work with it. I needed to take it and extract out what little product was made out of it. And to do that, it took nearly a full day just to work with. I mean, this would be from me getting up early in the morning, running this reaction, and then by the time I'm going to bed, I'm still not even done with it sometimes. And at this point, I was so confused that I just didn't know what to make of this. And I stumbled across this YouTube channel called Explosions in Fire. This is an Australian shitposting chemist who synthesizes explosives in his backyard. And what better man to go to for sage advice than him, right? Well, in this video, he's talking about how scientists hold grudges against certain chemicals, certain things that they work with. And organic chemists have their own special grudges. Some common ones are like hydrofluoric acid, which like eats through your skin, obviously not a good thing. And also, the physics department. But he's got his own grudges. Some of them are understandable, but then there's this one that kind of stood out to me. He doesn't like anything that's yellow. And he says this because, well, things that have been yellow in the past that he's worked with were just an absolute pain to work with. He just could not get good yields. It didn't work like ever he wanted it to. And it just smelled like crap every single time. So what was up with this? He termed it yellow chem, and he just made this grudge against yellow chem because every time he tried to work with it, it didn't work. Well, this was strange to me. That doesn't really make sense. But when I look back at my reaction, I had garbage yields. I had a product that was so difficult to work with, it was frustrating. And on top of that, it looked yellow. So that can only lead me to the conclusion that, well, yeah, maybe yellow chem is really that bad. And this guy was right. This random guy, I've never even met him before, but he's telling me that yellow chem is bad. Maybe he is right. But it doesn't matter. We're scientists. We encounter barriers all the time. We just got to get to the other side. So I did this reaction. I completed it. I got this like 10% yield, and I move on. But I did learn the second lesson of this research, which is that it's okay to hold a grudge. I mean, holding a grudge against this yellow chem isn't a bad thing because if anything, I made it out to be a challenge. I'm a pretty competitive person, so if I see a challenge, I'm going to tackle it as hard as I can. So this yellow chem, it was going to be the challenge for the next 3 years of doing this project. All right, but we have this next product now. Hopefully you've realized by now that organic synthesis is not as easy as Legos. And here's just another case why that's true. We can't just add on that other fluorine group because this hydrogen is just too stubborn. We need to replace it with an atom that's a lot more likely to add that fluorine group on there. So that atom is going to be bromine. In the second step of our synthesis, we're going to react this compound over here with bromine liquid in a solvent called DCM. We let that serve for about 30 minutes, and then we have to get rid of any excess bromine, and it makes acid when you do that. You have to get rid of the acid, and then you have to get rid of the solvent. So that's a whole like 2, sometimes 3 hours just to work with it after the reaction's done. But eventually you'll get this molecule that I call the dibromide. Notice how there's 2 bromines on here because we added those 2 in there. After that, we'll redissolve it in a 2-solvent system. So we have DCM and ethanol. And we'll add in a base called potassium hydroxide, which we've seen before. It's just going to do the job of kicking off one of these bromines and giving us this molecule on the right, which I call the bromide. Now this reaction took 3 hours to run, so a pretty long reaction. And then I had another about 2 to 3 hours to work with it after it was done. What was this molecule like? Well, this is what it looked like. And it's a pretty cool looking molecule. I mean, this orange crystalline product was just neat to look at. And it fluoresced a yellow again. And it was also orange in solution. So it was weird to me that as a powder, it'd be yellow, but in a liquid, it would be this bright orange emission. And that was neat. But this is orange, but it's just yellow chem in disguise. It turns out that this was absolutely garbage, just like the first step. I mean, I had 30% yields, and that was not good, but it seems better than the first one. But other people have done reactions similar to this one. And once again, they're getting 80 to 100% yield. I'm getting a fraction of that. And once again, this project is just being mysterious, it's being confusing. The best thing
All
I can
right,
do is
there
just
you
blame,
go.
oh, the best thing I can do is just blame it on the aliens and move on. And on top of that, we had a difficult workup, isolation, purification, once again, just like the other yellow chem step 1 synthesis. And well, we just can't do anything about it. We just got to keep pushing through every single time. Once again, I say it looks yellow. You might have said it looks orange, but this is, trust me, orange is just yellow chem in disguise. We come to the same conclusion that yellow chem is bad. Here I've solidified my grudge against yellow chem. I've seen it as a challenge, and now I got to keep pushing through. Here I've learned the third lesson, which is that if you can't jump the hurdle, you got to run through it. I mean, we encounter barriers in science all the time, and you have to find a way around it. But we could not find a way to better these two reactions. The first step and the second step, just bad yields every single time. So the best we could do is just force our way through it. We ran the first step 50 times and the second one 30 times. That is a lot of times for running a single reaction. I mean, I thought it was just like Legos, right? If you just put 2 bricks together, you get a neat thing. And I expected, well, I'll just run it about 5 times and call it a day. I wouldn't even have to worry about it. And then 3 years later, I ended up running it 50 times. So it should show you how complex organic chemistry can be. Luckily, I don't have to run through the hurdle every single time because in the step 2, I found a new way around it. So I won't go into too much detail about this, but this reaction takes about an hour and there's absolutely no purification necessary. So I actually ended up jumping the hurdle by just using a different reaction. So this is getting this product over here to the bromide, and it made it so much easier. But this was only a recent finding. I found this out winter term of this year, I believe. So for 2 years straight, I was running that other truly yellow chem synthesis, which was giving me really poor yields, which is why I emphasized it more. All right, but we have this bromide, and we can move on to the next step, which is going to be adding that other piece on there. And now, hopefully the Legos, I hope if you understand, it's not as easy as putting 2 Legos together, but it's still a good enough analogy that we can bring it back. And then in step 3 of our synthesis, we take the bromide, and we're adding on this third fluorine group. This is a base called potassium terpbutoxide. It's just going to do the job of pulling off one of these protons and making the reaction go forward. And we're using a new solvent called DMF, but remember, this is just helping everything mix together. And we'll get our final 3-component structure in the other end. All right, now this was an absolute pain to work with, just like everything else, because it was yellow. So what we decided was that we're not even gonna bother trying to purify this. We're just gonna take it to the next step, not even worry about trying to get it by itself. So we go on to the step 4 of our synthesis, which is making the radical. If we take that product, that 3-component structure that we had from before, react it with some base, it'll pull off that hydrogen, leaving behind a lone pair of electrons. But we don't want a pair of electrons. Remember, a radical is a single unpaired electron. So silver will do the job of plucking away one of those electrons from the other, leaving behind the radical indicated by the dot. And this is our final product. It's our BDAA radical, and I've made it. What did it look like? Well, it was this yellow color that if it was like in solution, it would be yellow, but as a powder, it was this dark green. And just this project has been so weird and confusing. So just seeing it going from yellow to green so easily was weird, but I just moved on. I didn't really make much of it. But it was just cool that we had the radical. What do we do with the radical now that we've made it? Well, we need to ask the question, how do we know that we made the radical? And for that matter, how do we know that we made anything else along the way? Well, if this was the 60s, I would just probably taste the radical and my tongue would disintegrate or something. And I'd be like, oh yeah, that was probably the radical. But we have more sophisticated methods now. And here's a laundry list of all those methods that I used. Really, the ones that I care about the most are EPR, UV-Vis, and mass spectrometry, because these are the ones that I use to characterize the radical. All right, let's take the radical and throw it into the electron paramagnetic resonance spectrometer, or the EPR for short. This is a somewhat obscure technique to most chemists, so I'm going to go through and explain it a little bit here. This is what the instrument looked like. I spent a lot of time down in the basement of Stites with this instrument trying to figure out how it worked. And then once I figured out how it worked, I needed to get a nice little spectrum out of it, which was even harder to do. But eventually I got the hang of it, and I know how it works. So here the sample sits, it's this tiny little tube, broken those tubes many times, but we don't tell Graham, oh, he's listening. But whatever, the tube sits right here. And there's electromagnets on either side of this. Those electromagnets are creating a big magnetic field around that sample. And then we're also hitting that sample with this microwave energy from this box up here. All right, how does this thing work theoretically? Well, here's a depiction of a radical. It's a single electron, and it has a spin associated with it. That spin causes it to have a tiny magnetic field around it. And if we put this radical in the presence of an external magnetic field, so remember those electromagnets are creating this external magnetic field, we can cause the radical to split into two separate energy states, a higher energy and a lower energy state. Now, if we increase that external magnetic field, we can increase the energy separation between the two radical states. And now we have some sort of control over the radical, and we can use this to our advantage. This is to show you, well, how an actual spectrum is being made by utilizing this energy difference. On the x-axis is the external magnetic field, and it's increasing as we go towards the right. And the y-axis is the energy. But really what matters here is the energy difference between the two radical states. Remember in the last slide I showed you, if we increase the external magnetic field, we should be increasing the energy difference between the two radicals. All right, and the bottom is going to be an example spectrum. It's just some random thing that I drew, but it should give you an idea of how the peak is being made. All right, let's start by increasing this external magnetic field. We're increasing the energy difference between the two states, and we're getting a flat line for the most part until we hit this sweet spot. What is the sweet spot? Well, it's the point at which the microwave energy that we're hitting the sample with is equal to the energy difference between the two radical states. And when this happens, some of that microwave energy is being absorbed in the sample, lost inside of it, and the EPR will detect that loss of energy and tell the computer to put a peak at this point. If we continue to increase the external magnetic field, we're moving away from this sweet spot and we get a flat line again. Now, depending on the radical, this area will show up different. So if it's specific to each radical you're looking at. So maybe it'll show up over here for a different radical or even further down for another radical. But the point is that we have a specific way to tell what radical we have. Okay, what does a real spectrum look like? Well, this is it. This is the EPR spectrum of my BDAA radical. And right away you can see it looks absolutely nothing like the example spectrum I showed you. I wasn't trying to deceive you, but the software does some funky things with it. The first thing is that, well, we're taking a first derivative of something like that example spectrum. So that's why you're seeing some negative Y values here. And also there's a phenomenon called hyperfine splitting happening here. So that's what these tiny little peaks and valleys are indicating, this hyperfine splitting. You can think of it like a fingerprint of the molecule. It's basically telling us where the radical is moving around on our molecule. And it's just a way of helping us analyze this radical. But what I want you to take away from this is that we have a radical, because if we didn't have a radical, it would be a flat line. And that was exciting because when I made this, I really wanted to test out right away whether I had the right thing. This isn't really a true way of telling me that, but it at least tells me that I have a radical. All right, now that we know that, we can move on to the next step, which is doing this thing called UV-Vis. I won't explain this to you, but it's a way of understanding or a way of checking its stability. So if we take a UV-Vis spectrum every single hour for say a day straight, and we get 24 spectra out of it, we can stack those spectrum on top of each other, and you should see some peaks getting smaller, some getting bigger because this radical is decomposing over time. But when we tried to do this, we found out that the UV-Vis, all 24 spectra, stacked perfectly on top of each other. This either meant that we did something wrong, or that we have an incredibly stable radical, maybe even more stable than BDPA. And I got super excited when we found this out because I was just like, well, this was unexpected. I mean, I didn't expect a incredibly stable radical. But there's even more that we can look into because what is the coolest part about this project is the glowy stuff. Does this radical produce light? So I went into this dark room, I switched off the lights, I took a bunch of vials that I had and put in front of a UV lamp and switched it on. And sure enough, you can look at this and see, yes, it is emitting this bright orange light if you irradiate it with UV radiation. And the picture does not do it justice. It was like so bright to me that I just could not believe it. But we have a stable luminescent radical, and that is exciting to us. That's so cool. But we still have one more data to look at. This is the mass spectrometry results. And we couldn't do mass spec here at Lawrence because this radical is just too heavy for it. So we had to send it off to Madison, and this is the form that I filled out for it. The most important part about this form is this molecular weight of 517. It's the weight of our radical. And what mass spec is telling us is the molecular weight of the compounds in our sample. And when we get our spectrum back, we should see a peak at 517. Well, if you take a look at the spectrum here, you can quickly glance at it and see there is absolutely no 517 peak. In fact, there's nothing even in the range of 517. Well, what's going on here? Does it mean that we don't have radical? Well, sometimes mass spec can break apart the radical into its components, into its fragments. So we try to look for its fragments in these little other area, the smaller area over here, but we don't see any sort of fragment that can correlate to the radical. And that definitively tells us that we don't have radical. Well, what's in here? There's something making that orange light. That has to be something, right? So we started looking at all these other peaks here. And we started with the biggest one, well, because it was the most prominent one. But honestly, we could not figure out what it was. Let's just make this problem even worse by having a peak in here that's so big that we can't understand what it is. Or you're like, oh, screw it. Well, we'll just look at something else then. Here's this 433 peak. What is that? What has a mass of 433 that we used? Well, that was the bromide. It was the starting material for the reaction that we made the radical with. Well, the data that we've taken so far actually does explain some of this because, well, when we looked at the stability test, we saw that the radical was so stable it wasn't decomposing. That's just because it was the bromide, not because it was the radical. The bromide doesn't decompose, and we fully expect that. On top of that, the fluorescence, that bright orange emission that we looked at, that also makes sense because when I synthesized this, I briefly mentioned that it luminesces in orange color. Okay, that checks out. Turns out we got this bromide, not the radical. And we hit a wall. I felt like I was sprinting uphill. I felt like I was doing so great and ran flat into a wall because I got the wrong thing. And here I learned the fourth lesson in my research, which is that you shouldn't count your radicals before they hatch. This was a big mistake of mine. I didn't take a look at all the data at the same time. I was just taking little bits of data and making my own inferences out of them. I should have taken a look at all the data at the same time to really know that I had the right thing. So this is a lesson to keep in mind for the future for me. But what do we do now? Well, we've ran into this wall. Just like in every other case, when we run into a barrier, we got to find a way around it. Let's take a look at the EPR spectrum that we saw from before. Just looking at this, you can tell that we still have a radical because if we didn't, it would be a flat line. And this gives us hope, it gives us motivation. We don't know if this is the right thing, but if we have some sort of radical, we have hope because we can go back and try to isolate the real thing, this thing that we're seeing in this EPR spectrum. So here's the most recent work that I've done for this project. I've isolated what I think is the real radical, emphasis on I think because I don't know for sure yet. It is this dark purple crystalline solid, and it's not luminescent. It's fairly unstable, which means I can see it turning from purple to green in a matter of a couple minutes. Now, this was the exact opposite that we set out to do, unfortunately, but nevertheless, we're gonna move on. We're gonna do all those spectroscopic analyses again. We're gonna make sure this time that we got the right thing, that we got BDA radical before we start doing any other analyses with it. And finally, we're going to get the word out by writing a paper. You might ask, well, how do we write a paper on a failed experiment? Well, it wasn't a failed experiment. It just had unexpected results. So first of all, we need to spread the word that yellow chem is bad. All right, this is probably the most important thing for me. We need to tell people that we've made this yellow compound called BDAA. It was a pain in the ass to make, and we don't want you to do it, but here's everything you need to know about it. But I guess Graham told me there's a probably more important part about this, which is that there's an anomaly. This molecule should have luminesced, but it didn't. And why did it not luminesce? Our job now is to figure out, well, why, like, what can we do to figure out why it didn't luminesce? And the best thing we have is computational theory for that. So we're going to compare, well, computational theory to what we see in this radical and try to figure out why this thing isn't luminescing so that if people try to design luminescent radicals in the future, they have a better idea of how to do it. Now, unfortunately, I didn't have time to do this because we ran out of time. So hopefully someone can pick this up in the future and finish it off for me so we can finally write this paper for this thing. We've been waiting for so long to write this paper. And with that, I'd like to acknowledge a few people, starting with Graham. I've worked with him for 3 years now. It's been a long time. He's acquired a new nickname every single year, as you can see right there. He's been a great mentor to me, and to put it plainly, he's made me a better scientist. So I'd really like to thank him for that. And of course, I'd like to thank the rest of the chemistry department and Lawrence University in general. Everything that I've learned in my classes, whether it comes to lab techniques or even a new way of thinking, has been super important for me and my research, and it's helped me get over some of these barriers. Finally, a special thanks to DMART and the stockroom. I've caused a little bit of chaos, quite a bit of chaos here in my last 3 years. I've broken quite a few things. And actually, I broke this really expensive glass instrument right before I left for quarantine. But luckily, DMART has always been super patient with me, and he's always super reliable. And he got a new rotovap and already installed it. And there's not even working in lab yet. So it just shows how dedicated he is to our department. And it's been essential to my research. Also, my lab mates, because every time I come to a barrier in my research, they've always been there to support me and help me over it. And finally, the ACS PRF and the Chandler Senior Experience Fund for sponsoring my research. With that, I'd like to leave you with one last lesson that I just could not ignore. It's probably the most important takeaway that you should have from this presentation, which is that yellow chem sucks. Thank you.
Thank you so much, Mick. I'm sorry my internet is a little bit flaky right now, but I will take questions from anybody. If you want to chat it, if you want to raise your hand, if you just want to speak up, I'm sure Mick will take a question from you. No questions?
I have a question.
Okay.
Mick, why do you have to put it in different solvents? I think I just never understood that. Like, what?
Oh yeah. Let's see if my keyboard even works. Technology's not working for me today. Where'd it go? There it is. All right. So the main reason for this is because DCM dissolves the dibromide, because DCM is a halogenated solvent, and our compound here is halogenated, so it makes sense that like dissolves like. But also because KOH does not dissolve in DCM. So ethanol will do the job of dissolving the KOH and then bring it into the DCM. It's just a way of mixing two separate things that aren't soluble in one solvent.
Other questions?
I'm kind of curious as to whether it's really flat.
Oh, right. Yeah, that's a great question. And I probably should have mentioned that, and I didn't. But here's a BDAA. Actually, it's even better to look at BDPA, because this is a known molecule. We've seen this. There's been plenty of analysis done on this. This is not a 2D molecule because of these hydrogens right here are bumping into each other. So it's you can imagine this molecule is twisting in this like 3D propeller-like fashion. So every molecule is twisting in the plane of space in certain ways. And that actually helps encase the radical even more, making it more stable.
Other questions?
I have a question.
Yeah.
Why is it that radicals can only undergo fluorescence and not phosphorescence?
Yeah, and so that has to do with the spin orientation. So electrons in the non-radical system, there's always going to be one electron staying in the ground state, while another electron is being excited into all these other states. And because that one electron is staying in the ground state, there's kind of like a reference for the other excited electron. So it can take multiple positions relative to the one in the ground state. Versus in a radical system, you have a single electron that's being excited, and there's nothing left in the ground state as soon as you excite it. So as soon as it goes up, there's only one orientation that it has, and that means that there's only one way for it to go back down to where it was.
Any other questions? If I'm not missing anybody, let's thank Mick again. Thank you so much. We will stay in this talk for 2 more minutes, and if you want to hold on, I will send you the link to Molly's talk over chat, or you can maybe see that go to Molly's talk or not, but we'll be moving over there in a minute or two. But take your time and say congratulations to Mick for right now.
Good job, Mick.
Thanks.
You did it.
I did it, finally.
Congratulations.
I'm sure you appreciated all your pictures, Graham.
Yeah, I really
these are
do.
the best ones I could find on the internet, so you can blame the internet for that.
Yeah, guess I could blame myself for not posting more pictures of myself.
Yeah.
Looking out, Mick.
Is the middle one undergrad or grad school?
Grad school. It's the Bentley Lab. I looked it up.
Is that in the Bentley Lab?
Yeah, it is.
Do you like my wood tick shirt?
Oh yeah, I honestly didn't even look at that.
That's gross, but kind of
It
cool
is,
too.
yeah.
This is the research that we want.
That's I think that was in undergrad though, because there's a
really?
set list from my band on the chalkboard behind me.
Oh, no way. Okay.
Yeah.
That's the main
Mickey-
reason why I had this picture of you shredding this guitar.
Yeah, that was a band I was in grad school from that
Ah,
black
okay.
and white shot.
I was going to use this to explain radicals because you're being very radical here, but it ended up taking up too much time, so I stopped that.
Mick, you should have used that handstand picture to explain spin flipping.
I was gonna. It just like it kind of cut away from the flow of my presentation, so I had to
That's a
take
good
it out.
idea.
I see.
I'm sorry to say I am going to need to end this one just because, I mean, I can leave, but it will only give you like 30 more seconds until I start the next one.
Deanna, do you want to transfer me to host and then we can hang for a second?
Sure.
Big brain. Graham always with that big brain move.
Maybe. Thanks, Deanna.